for this super nice presentation, and I'm really glad to be here for my first time in India. Just one complaint that is colder than in the Swiss Alps. So I didn't expect that. Okay, so my course will be a Bork course. Okay, so maybe slower than the other, but so I prepare really for to explain things. And okay, so the broad topic will be this kinetically constrained spin models that have a fancy name, but as I'll explain very slowly. And so the origin of this model comes from statistical physics in the middle of the 80s, or condensed matter physics. And so in condensed matter physics, there is still a big major problem that is understanding the so-called glass transition. When you take a fluid and you cool it very rapidly at some point, so it does not crystallize, and at some point, experimentally, you observe that becomes a glass. And still, I mean, physicists, they don't really understand well this transition. And in particular, there is an ongoing, this big grants, Simon's grant, $20 million for a group of physicists around the world. And the title of the grant is Cracking the Glass Transition. However, this model, although they have an origin in, in physics of glasses, they also appear, naturally in other contexts. David Aldous, who together with Percy Diaconis was the first to prove a rigorous result about them, proposed them as a, little model for storage in computer science, storage algorithm in computer science. But as I'll show, they also appear naturally in some random walks on group of matrices. Okay, so not really so much is known about them, and basically I'm going to tell you what is known today in this 3 lecture plus the research talk. Okay, so I will start, just to be sure that we are all together. I will spend the first 10 minutes on super basic stuff on Markov chain, reversible Markov chain, in such a way that from there we can move easily to models. Okay, so please, you should tell me whether I'm writing too small. Okay, so because I understand that from the back rows it's not so easy to see. So I take the hypercube, okay, and then I'll do. So I want to do Glauber dynamics, the super basic Glauber dynamics, a discrete time basic Glauber dynamics on the hypercube, and so this is a reversible chain. So I fix a parameter p between 0 and 1. And so suppose that omega is the current configuration. So T now is discrete. Maybe an N here. And then the chain goes like that. So you choose a coordinate. So with this notion, I mean all the integer from 1 to n, okay? And then erase what the current value omega t at I, so the coordinate omega t, and replace with a new coordinate 0, 1 that is sample, so 1 with probability p, so you toss a coin, and 0 with probability q, so resample from Bernoulli p omega I. Okay. Okay, so this is an elementary chain. Actually, it's a product chain because on each coordinate you have a independent, two-state Markov chain between 0 and 1. Okay, and so it is reversible with respect to the product measure that I call mu. So this is the product measure of the Bernoulli P. Okay, and we can talk about mixing time and relaxation time. So mixing time is, loosely speaking, is how many steps you have to run the chain in such a way that starting from the worst configuration, you are close to the stationary reversible measure in total variation. Okay, so T mix is the max min T such that the total variation between the distribution, say, starting from omega minus mu in total variation is less, well, conventionally is 1/4. Okay. Okay, so that's the mixing time. And okay, so there is another notion of interesting length time scale, which will be more relevant for the model I want to discuss, and this is the relaxation time. So relaxation time is taking like that. So so the matrix, so the transition matrix has real eigenvalues that are usually in absolute value less or equal than 1. There is one that is 1, and then there are the others. And then you take the relaxation time is 1 over the gap or spectral gap of the chain, okay? And the gap is the mean of 1 minus lambda eigenvalue lambda less than different from 1. Okay? Okay, and so actually the relaxation time, okay, so this is in the discrete case. So actually we would like really to work in many situations on an infinite graph. Okay, so here there is no geometry, of course. Okay, so one end could be just the vertices of any graph with n vertices. But if we want to take a graph that is infinite, so we need to move to continuous time, and then the continuous time version. So the continuous time version goes like that. So let nt a Poisson be a Poisson process of rate n, okay? And then define, say, xt, the chain in continuous time, as omega nt at time nt. I don't remember whether, yeah, time is down below, okay? So this is a chain that is accelerated because, so on average, you have n update in a unit time, okay? While there, on a unit time, there is only one update, so it's accelerated by n. And, okay, so a very convenient way to consider this chain is not by considering a global plus Poisson process with rate n, but using the fact that the sum of Poisson is still Poisson. Imagine that at each coordinate there is a Poisson clock of rate 1, okay? And when the clock rings at coordinate I, you erase the value, the current value at I, and you replace with a new one, random one, sample from the Bernoulli distribution, okay? So there is a graphical construction then, what is called graphical construction. So you have this Poisson clocks at I in n, rate 1. Rate 1 Poisson clock, okay? When clock ring at I, resample omega I, or actually xti. Okay, so the ith coordinate, okay? Resample from the Bernoulli distribution, okay? So the advantage of this construction is that now it works perfectly if you take any infinite number of coordinates, okay? And typically this will be always the graphical, or it's called graphical or Harris graphical construction that we will use also for our model. So I'm going to finish this part before introducing the real model by recalling what characterization of the relaxation time in continuous time, Diuchlit form, and Poincaré inequality, just to put things in order. Okay, so again, for this chain, you can talk about the mixing time, you can talk about the relaxation time exactly as before. And okay, so there is a generator. So this Markov chain has a generator L, and you can compute the form of this generator that, so usually the generator is the transition matrix minus the identity. Okay, you do the computation in this case here, and the generator becomes as the following form: sum I from 1 to n of the mu I f minus f of omega. Okay, where mu IF means that you are taking the average of f of omega only with respect to the ith coordinate. Okay, so it's, if you want, a conditional expectation on given all the coordinate outside I is a trivial because the measure is a product measure. Okay, so the Diuchlit form which is just the scalar product f minus LF, okay? And the scalar product is the standard scalar product for reversible Markov chain, okay? So this takes the form, so usually this I will denote like df, maybe Prasad in his lecture too, and this takes the form of sum over I from 1 to n in this particular, for this particular chain, this Glauber chain, is the average. So the average, I'll usually use the notation mu of something is the average of that something, okay? And then I take the variance with respect only the coordinate I of f. Of course, this quantity does not depend on the coordinate I, but depends on all the other coordinates, and on all the other coordinates I must average. Okay. And then so if you recall what the relaxation time is given by 1 over the gap. So the gap are given in terms of the eigenvalues. If you remember the variational characterization of the eigenvalues of a symmetric matrix, then you get that the relaxation time okay, is the best constant C in the Poincare inequality maybe I should not write over there. And maybe here. The Poincare inequality. Yeah.
I'm kind of unfamiliar with this form. Can you motivate a little bit? What would you like to say that?
Oh yeah. So so the eigenvalues. So L is a matrix, okay, and is a matrix that is symmetric with respect to the scalar product given by mu. So the scalar product Fg mu is equal to the average of Fg. Okay, and so if you want to compute the eigenvalues of L, well, you can use the minimax, so the variational representation in which you have to compute the so the quadratic form of L, which is the Diuchlit form, well, minus L, okay, and compare it to the L2 norm of a function. The L2 norm of a function, if the function as mean 0, is just the variance. Okay, that's why. So we are interested in the Diuchlit form. So since the eigenvalues are, say, the eigenvalue, so in this case L is a negative, is an operator, is a matrix with eigenvalue 0 and then other eigenvalues that are negative. So the gap is the absolute value of the first negative eigenvalue. Okay, and the relaxation time is the inverse of that. Okay, so this is the best. So if you recall the minimax principle for eigenvalues, this is, so TRL is the best constant in the Poincare inequality, which is variance of F less or equal than C, the Diuchlit form. Okay, and the property, and of course the reason why we are interested in this relaxation time is if we compute the variance of the semigroup of the chain applied to a function. So what we get is that this is exponential minus t over TRL, the variance of the function originally. Okay, so it's a trivial computation. Okay, just write everything in eigenfunction. So expand all the so the function in the eigenvector of L. Okay, use and do a trivial estimate. Okay, so in a sense, this time scale rules the approach to equilibrium in the sense that this function becomes a constant in L2 sense. Okay. So for this particular chain, we can compute everything, right? Because it's a trivial chain, and actually, if you recall that for since the measure is a product measure, okay, so this is what I call mu I. Okay, so since we are dealing with independent variables, the total variance of F is always less than the sum of the average of the local variances. That is a general fact about product measure, okay? But this expression here just happens to be the Diuchlit form, okay? And therefore, in this case, TRL is 1, okay? Of course, you could have computed that TRL was 1 by in many other ways, okay? But, okay, so, right, so for this chain, we have that the relaxation time is 1. There is another quantity, before going to a more interesting chain, which is the following. So relaxation time is good in the sense that gives you a control on how fast you go to equilibrium in L2 sense, okay? But maybe you want to prove, you know, a result on in a stronger norm, okay? And then, so you can use this observation. So, so compute, for example, yeah, so compute the expectation starting from some configuration omega of the coordinate, see, so t is down omega I, okay? So for t large, this quantity should converge to p, right? Because at equilibrium, this average is p, and you would like to take that and maybe to compute a max of omega, okay, which is a stronger, is another notion, but in a sense stronger than the other one, okay? Well, this is also going down exponentially fast. Why? Well, because as soon as the Poisson clocks of I rings, then this variable is replaced by a Bernoulli variable that has mean p, okay? And therefore, this difference is controlled by the probability that up to t, the Poisson clock of I didn't ring, and this is exponential in t. Okay? Good. So last thing is, for this chain, you could also compute a more sophisticated quantity, not the relaxation time, namely the best constant in the Poincare inequality, but you could also consider the logarithmic Sobolev inequality that Prasad will tell you about in the next lecture. And in this case, for this chain, this constant is also very much under control, and this constant really allows you, in general, for more general chain, if under control, then allows you to go beyond L2 convergence to better to like L infinity convergent or LP with P large. Okay. Unfortunately, for this kinetically constrained model, this constant I will show soon, this Sobolev constant, logarithmic Sobolev constant, behaves very badly. And in a sense, the relaxation time is basically the only quantity that is under control. Okay, so this is the situation. Now I will go to this kinetically constrained model that can be constructed exactly as we did. I mean, following the scheme that we use for this trivial situation. But in the following, in the following way. Okay, so take a graph. Okay, so let's say for a second finite and connected, and for most of the result they actually hold for when G is a box. Is a box of, say, ZD, okay? But there are also results for more general graphs and one specific result for trees, okay? And you consider omega, which is 0, 1, V, okay? You fix P again. Okay, and you do exactly the construction that I described before in continuous time, namely to each vertex you attach a clock. When the clock rings, you try to resample the value at that vertex from the Bernoulli distribution. However, now comes in to play the constraint. So constraint so in the most general case that I will, but maybe I'll describe it on ZD, not on a general graph. So the constraint more or less is the following. So the clock at X, so a vertex X ring, okay? And you sort of try, so you would like to update the coordinate at X. However, first you check what are the coordinates in a neighborhood, maybe a large neighborhood, depends, of X, but you don't check the state of X itself. So you only check what is around you. If what is around you satisfy a certain constraint, then you do the resampling. If not, you forget about the resampling and you wait for another ring. Okay? That's the general scheme. That's the general scheme. Okay, so I'll spend a few words later. Yeah. Okay. So, and I'll give explicit example on ZD where it's more clear. But so what is essential is the following: is that the constraint checks what is around you, but does not check your state. Okay, and if some constraint is satisfied, then you do the update, exactly the trivial update as before. Otherwise, you forget it. Okay. No. Sorry. Since the constraint does not look at X itself, it is easy to see that the chain that you get is still reversible with respect to the same measure, product measure mu. Okay? If instead you also check your state, so the state at X, then this reversibility is completely lost and you're looking at completely different model. Yeah, completely different model. Okay? So constraints usually are indicated by Cx, okay? And so Cx takes value in 0, 1. They are sort of hard constraint either, and if Cx is 1, do the update, update. If not, forget it. Okay, that's the general scheme. Okay, and usually, so we say that a ring, a Poisson ring at the clocks, let's say at X, is legal if at that moment the corresponding C sub X is 1. Okay, so let me give example. And then I'll write down, the Dirichlet form, etc. and see what happens. So, example. So, as we said, the construction, can work, in a finite box or can be in the whole lattice. So for the moment, I forget about whether we are working in finite or infinite volume, which, however, is important distinction, and we'll be careful later on. Okay, but so just for the example, is one neighbor model. One neighbor model, Cx is 1 if at least at least one neighbor of x is 0. Okay? So immediately this says that for the one neighbor model, the zeros are the good guys because they help you to do updates. Okay? The ones are the bad guys. Okay? Then, second moment, two neighbor model. So this is at least 2. Okay, of course here we need, I mean, in order to do something non-really trivial, we need to be, say, at least in 2 dimensions, d at least 2. Okay. Okay. So so the third example is the east or west model. Okay, so I prefer here, I mean, originally it was written as east. I'll explain why east-west. Okay, but I prefer here to add the convention west. Okay, so in this case, D is 1. So we are in 1 dimension. And Cx is 1 if omega x minus 1 is 0. So if your left or west neighbor is 0. Okay, so originally it was if your east neighbor is 0. Okay, but of course it's just the same. Okay, so this is oriented. This is oriented because in order to check whether you are allowed to do a resampling of your state at x, you have to look at, well, your west, okay, here, okay? While in one neighbor, okay, I have just to check in 1 dimension the right or left neighbor, and if one of them, at least one of them is 0, then I'm fine, okay? We will see that this orientation changes dramatically things, okay? So people also, you should wait, Saturday I'm giving this talk, okay? Yeah, you should wait for that. But actually, you said something that is very true. Namely, here there should be some monotonicity, right? Yeah, exactly. So I'll explain that. Okay, so so another model that has been quite popular in the among bootstrap percolation people is the Duarte model, invented by physicist Duarte. Model, say D is 2. Okay. And so Cx is 1 if, okay, so this is x, so there is the north, south, and west, north, south, and west, okay? So if 2 among these 3 guys are zeros, so means this guy, or this guy, or this pair, or this pair. Okay? So this is also oriented because, so you look either to up, down, or left, but not right. Okay? So in a sense, so maybe we can stop at, sorry. So the last important model is the northeast model. Northeast model. And d equal to 2, okay. So Cx is 1 if omega, omega of x plus well, say, sorry, is one if north and east neighbors are 0. So in this case, x is here. You have to check whether these two guys are 0 in order to have a legal update. Otherwise, you are not allowed. So it's quite clear that this model must be related to oriented percolation into dimension. No? And actually it is. Okay, so before giving a general definition, okay, so about this monotonicity, okay? So it's clear that, say, one neighbor mode is less constrained than the east. It's more easy to have C sub x that is satisfied. The two neighbor model in 2 dimensions is less constrained than the Duarte model, because you are forgetting about in the Duarte model, you don't check the west neighbor. And that the northeast model is more constrained than say, the 2 neighbor model, because you require exactly the north and east. Okay, so there is some ordering. Yeah.
What is the initial line?
Sorry?
Starting consideration.
I'm just describing what are the constraints, okay? So then we have to be super careful about, whether, so irreducibility issues, okay? Because there are constraints, so maybe you cannot go everywhere in the state space, okay? And so we have to be careful about the initial condition and which kind of result we can prove are reasonable to prove or not. Yeah, absolutely. Okay, so, okay. However, so I would like to, so before, those are just a series of examples. Let's see. So at least, well, actually, I could also formulate this on general graph, but it really doesn't matter. So on ZD, general formulation is the following. General formulation so fix a finite family U so this is a finite family of subset of ZD. So UI is a subset of ZD minus the origin, okay? And they are finite, okay? For example, in this example, you take the one set of the neighbors of the origin. In this example, you take the 2 subset of the neighbors of the origin, etc. Okay? Okay. And then, so given omega in D, you say that C is 1 if C0 omega is 1, if there exists UI such that omega restricted to UI is 0. Okay? So this is the constraint for the origin, and then you do trivial translation and you define the same constraint for all the other vertices. So they're translation invariant. Okay? Okay. Okay, so this is a general, general class, so everything depends on this. This is called an update family, and then you would like to study the corresponding model. Okay? And actually the topic of Saturday talk will be universality result for this model according to certain geometric feature of this family here. Okay? Okay, so the Dirichlet form now takes the form some x of mu of c sub x omega var x f of omega. Okay, where again, this is the local variance computed with respect to the Bernoulli measure at x. C sub x has been defined, and then you average all the rest. Okay, and you have to sum over, x in V. Okay, and of course, if we are on the infinite lattice, maybe f is better to be, say, of compact support, so it depends on finitely many coordinates, so that this variance becomes 0 after a while, and this sum is a finite sum, actually. Okay. So the rest really goes through. So the Harris graphical construction goes through, and so you get a very well defined in infinite volume. In finite volume, of course, you have to be careful about irreducibility problem. Okay, so for example, ability issues. Okay, so let me take an example. So let us take one n, so this is 1 now. Okay, and let us take, for example, the one neighbor model. So one neighbor model, you need at least a 0 to your left or right in order to do an update. So it's clear that if you start from all ones, you never move, okay? So this is a trap. But if you start with at least 1 0, you will never able to reach all ones, right? Because, so it's not a trap, sorry. So it's just a fixed configuration. So if you have at least 1 0, you will not able to destroy all the 0, because the last 0 will never be able to flip to 1, because it needs, a 0 either to the left or to the right. Okay, so here there is an ergodic component, which is all the configurations that are not identically equal to all ones, okay? So one possibility is to study the one neighbor model in finite volume, in a finite region, on this ergodic component, okay? Right? And another possibility, which is much more convenient mathematically, and that occurs sort of naturally, even when studying the infinite lattice, is to put boundary condition, as is customary in spin system. So boundary condition here that would immediately restore ergodicity is to say that, say, one vertex is free to flip always. There is is unconstrained. And typically you could say, for example, that this guy here is free to flip. Because if this guy is free to flip, this guy is able to inject 0 into the system, and then you're done. Okay? So, for example, if you consider the East model, so the East model means that you have to look at, so you always need your neighbor to the left to be 0 in order to be updated. Then of course, I mean, if you start with some initial condition in which the leftmost 0 is here, okay, so here there are all ones, and then something, then this region here will never be updated, okay? And because there is no left zero here, okay? And then, in a sense, the chain will stay equal to 1 here, and then will be a good ergodic chain on the rest, okay? Okay, for example, so the northeast model, say in a box, okay? So the northeast model, in order to flip, you need the north and east neighbor 0, okay? Well, then boundary condition means that all this guy should be able, boundary condition that restore ergodicity inside the box means that all this guy should be able to flip freely without any constraint, because if that is possible, then this guy can become 0, then the next guy can become 0, etc., and you can proceed, okay? And you have a reducibility, okay?
So if you fix them to 0?
No, well, or either you fix them to 0, or they are free, and therefore you can put all 0 here, then you can put a 0 here, and then you proceed and you continue, okay? All right? Okay, so clear for a general rule, okay? So boundary condition could be a little bit involved, of course, depending on the geometry. There, okay, thanks. Oh, okay. So, yeah, maybe a few words, sorry, I just wanted to reply to a question about some monotonicity. So, the zeros in the system are the sort of, are called also facilitating sites, okay? Because they facilitate movement, where movement dynamics means that there are some spin flips, okay? However, this chain do not show any monotonicity in the following sense, the monotonicity that you can observe, for example, if you consider Glauber dynamics for, say, the easy model. So if you take two initial configuration, omega and omega prime, and say that omega has more 0 than omega prime, it's not true that this ordering, partial order, is preserved by the chain, okay? So there is no monotonicity in this sense, because if you inject more 0 into the system, this more 0, they facilitate more flippings, which means that certain other 0 can flip back to 1s, okay? And so, okay, so there is no monotonicity, which is a major issue, because you know, a lot of tools that are based on monotonicity, they get lost. Okay. However, there is another monotonicity that maybe is one that you were observing, and is monotonicity of the Dirichlet form. So it is quite clear that if Cx is less or equal than Cx prime, then the Dirichlet form F is less or equal than the Dirichlet form prime, just because these are non-negative quantities, okay? So in particular, if you recall that the relaxation time is the best constant in the Poincaré inequality, variance of F less than the constant Dirichlet form, times the Dirichlet form, then immediately we can get like an ordering between the relaxation time of the various models. For example, we get that the relaxation time of the one neighbor model is certainly less or equal than the relaxation time of the east model in the one, okay? And for example, the relaxation time of the two neighbor model is less or equal than the relaxation time of the Duarte model. Etc. Sorry? Oh, from d equal to 2 to 3? Well, also, no, because, for example, if you ask that two of your neighbors are 0 in 3 dimensions, okay, then you can compare it with two of your neighbor on, say, on the horizontal plane only, okay, and this is more constrained, right? And therefore you get also some monotonicity in that sense, yeah. So you can play with that. Okay. Of course, I'm writing this inequality, but I'm not checking whether this quantity are finite or infinite. Nobody is telling us whether the relaxation time is finite or not, because now there are constraints. Who knows, right? So let me give immediately an example of a case in which the relaxation time is actually infinite. Okay. Let us consider the northeast model. Okay. And suppose that P, the parameter P, is bigger than the critical value for oriented percolation. I'll explain what that is. So, oriented percolation in 2 dimensions actually side oriented percolation, just to be very precise. Okay? So oriented percolation is the following. On the 2-dimensional lattice, you assign at each vertex value 0 or 1 with probability, so 1 with probability p and 0 with probability q1, which is 1 minus p. Okay? And then you ask, and then you consider, so the oriented cluster of a vertex at the origin is the set of ones that can be reached by the origin using an oriented path that either goes north or east. Okay, like that. Okay, so it could be this guy, this, and that. Okay, let us include 0 or not, that really doesn't matter. Okay, and then you may ask for a given p whether the probability that the origin is connected to infinity with an oriented path of ones is positive or not. Okay, so it can be proved that for p larger than a critical value that is not known, theoretically, there are, bounds. This probability is positive. Okay, so there is a nice review of many years ago by Duret about oriented percolation. And so now, so suppose that we take the northeast model, but P is bigger than this oriented percolation threshold. So this means that with probability 1 inside, if you sample an initial configuration from the stationary reversible measure mu, so then with positive probability that there are infinite oriented paths of ones. Now, this oriented path of ones, they cannot move. They cannot be updated by the chain because each vertex on the path has at least either the north or the east neighbor that is 1, and therefore, is constrained, right? Is locked. So there are block configuration in the reversible measure, and this immediately implies that you cannot, exponentially converge to to equilibrium, in infinite time, and therefore the relaxation time is 0. So a major question, I'm finished, is a first major question is, given P, okay, is the relaxation time finite or not? Okay, and this we'll examine the lecture, and then you would like to ask, if it is finite, what is the form of function as a function of P? Okay, and then the much more complicated question is, suppose that I start the process from some, distribution, maybe even product distribution that is different from mu, maybe as P prime, Q prime, okay? Is it true that locally that goes on converge to mu? If yes, how fast, etc. Okay, so this topic will be discussed next lecture, and the third lecture I will concentrate on some peculiar, feature of this model, and this model is a key to understand, very general update rules. Okay, thank you.